Hi, welcome back to Physics Teacher. And today I'm going to teach you how to analyze the physics of this. Alright, so before we get started, I'm going to show you the software that I'm going to be using. It's Vernier Video Analysis, and they have some different softwares that you can use. They have a 2.0 Web 2.0 tool that you can use, which is great if students have Chromebooks, because they don't need to download and install anything. They have apps, so if you have an iPad and want to use it there, you can do video analysis on your iPad. I'm going to be using the Logger Pro software, which is used with a lot of their equipment to do labs, but it also has a video analysis component to it. And I'll put all of the links to this website, as they also have an introductory video to how to do video analysis. But I'm going to show you and give you tips and tricks to how to use it to analyze the physics of video games. Alright, so before we start analyzing a video, we need a video. So let's go back and look at the video I showed you at the beginning. Now, it's important when you're trying to choose a scene from a video game, the limitations that we have. So the program, the video analysis program, is essentially a program used to analyze the position of an object over time, and that can be used to determine the object's velocity or even acceleration. That's it. You can't directly measure energy or forces or momentum. Those will all have to come from the position time data that you get from your video analysis. So let's look at this scene that we looked at in the beginning. Alright, so right there, let's say you wanted to figure out how fast that train was moving. Well, watch again. Let me show you in slow motion here. As the train moves forward, you can see the fence is moving backwards. So our point of view is slightly moving in the same direction as the train. So if you were to simply try to look at the position of the train on your screen, which is what the video analysis software does, it wouldn't quite give you the correct speed of the train. However, there is, of course, ways around it, and I'll show you how to do that. What we're going to do to analyze this part is measure both the speed of the train and of that fence there. And we'll essentially use relative velocities to add those velocities to figure out the speed of the train. But let's look at another example of the train. Right here. So in this case, the train is coming towards you. It's coming out of the screen. You can't really measure speed that way, because on your screen, the position of the train doesn't change. It's always on the same spot. So if you try to measure speed, which is change in position, it'll seem like the train isn't moving at all. Now we know it's moving because it's getting slightly bigger and bigger and bigger. And if you want to do some really complex analysis on your own, looking at how the area is changing over time, you can certainly use the software to measure time, but you're going to have to deal with everything else yourself. Now, we are going to talk about measuring distances as well in the software. So how you measure distance is you need something as a reference point. So your software looks at this and it measures everything in terms of pixels. Well, we don't want to know how many pixels the train is moving across over time. We want to know meters per second, not pixels per second. So we need a point of reference. Maybe, for example, you know what car that is. And if you know what car that is, you can look up its dimensions online. And therefore, maybe you know the length of the car. And so you can tell the software, this is the length of the car. This distance from this pixel to this pixel is whatever, 3 meters. And then it will be able to judge everything else in terms of that. And so you can actually measure the size of other objects. Alright, now in this picture, if you wanted to find the speed of the car, that you could do because the car is moving left to right. You can find the speed easily of anything moving left to right or up and down or a combination of both. It's just into and out of the screen that you can't do. So continuing. Okay, right here, same thing. In this case, what we could do if you wanted to say measure the force on the car, you can't directly measure force, but there are a couple of ways around it. Right? If you remember, say, Newton's second law, force equals mass times acceleration. You can figure out the acceleration of that car and find an average force over time, over whatever time interval you choose. You can also use impulse equals change in momentum. So if you know that time interval and it's change in momentum, which has to do with velocity, which the software can get for you, you can figure out, again, average force over a certain time interval. Okay? And it's the same thing with dealing with energies as well. If you know the speed, you can calculate its change in kinetic energy, which is equal to work done. And if you know the distance over which it stops, which the software can figure out for you, again, you can then use that to figure out the average force. All right, so let me show you how we're actually going to do that. All right, so here's the Logger Pro software. Now, if you're using the Web 2.0 on Google Chrome or your iPad, it might look slightly different, but all the features will still be there and the same. Now, the first thing we're going to do is insert our video. So by now, I'm assuming you've all taken a video of whatever game that you want to analyze. I'm not going to tell you how to do that. There's lots of ways to do a screen capture. If you're interested, you can always ask me questions in the comments. But we're going to insert that video. So we're going to go Insert, Movie. Alright, so now we have a few things. Here we have our video that we can analyze. We have a data table and we have a graph. And you can rearrange the sizes of them if you like. And what we're going to do is we're going to find the part that we want to analyze first. So I'm going to start with this one. Right there. We want to find the speed of that train. And then there's a button over here. It says Enable or Disable Video Analysis. So we're going to enable that. And notice a couple things have come up. We have X and Y, and X velocity and Y velocity. Now I'm going to need to do a couple things. I'm going to need to set an origin. So where am I going to have an origin? It doesn't really matter where you have your origin. Here, let's put the origin all the way over here. Okay. And then I can click Add Point. Now I'm going to choose a point on the train that I'll just keep repeating. So for example, I can choose like this light. Now as I click, you can see I've gotten a point here, an X and Y coordinate based from this origin, and it's also plotted it as well. And what it also did is it skipped to the next frame. So I'm on the next frame, so I'm going to click again, and next frame, click again, click, and you just keep going from one frame to the next frame to the next frame. As many data points as you like, and preferably taking a little bit more time to do it a little bit more accurate than I am doing it right now. Okay, now it's gone past. Alright, so we've got two graphs here, a blue one and a red one. So what are those? Well, our blue one is our Y component. So it's looking at your vertical components going up and down, because you notice if this is our Y and X axis, it is slightly going up. And that's because it is slightly coming, like the view or the angle of the camera is slightly coming out and up. So there are going to be some errors when we calculate that velocity. Okay, doing this sort of is like a Fermi problem, right? You need to figure out, okay, how are you best going to get as much information as you can to get an answer as accurate as possible, but also be aware of the errors that are going to be involved in that. All right, what else is it doing? These are all in pixels, Right? We haven't actually chosen anything to tell it a distance scale. So we're going to go here and click on Set Scale. And now the question becomes, what are we going to choose to set that scale? I mean, I could look at this fence and I could say, well, it's about 1 meter long, and I could set that. But then think about this. If you're to take that fence and sort of move it over, translate it to where the train is, it's almost the same size as the train. So you'd be saying the train is 1 meter high. Right? It's best to choose something as close to the object you're analyzing as possible. So in this case, it'd be great to choose the train itself. So I can put a line, and I could go on Google and say, like, what's the average height of a cargo train, right? And then you would type in that height. Okay, so I'm going to estimate 3 meters. And once you do that, everything is automatically converted to meters instead of pixels. All right, now I want to know its speed. Now this is a DT graph, or a position time graph. The slope is the speed. And what you can do to get the slope, I want to know the x, so it's horizontal. So I can go up here and do a linear fit of our x. You click OK. So here's your equation in your mx plus b, where m is your slope. So it says it's negative because it's moving towards the origin. 7.5 meters per second. You will have to change that yourself to kilometers per hour if you like, which is actually only 27 kilometers per hour. Okay, but remember, it's obviously going faster than that, so why are we getting something so small? Couple reasons. One, again, the angle of the camera. What we could do to help is also do a linear fit for our y. And then we can sort of add them using Pythagorean theorem. Right? X squared plus y squared equals our velocity squared. As if those are x and y components of velocity. Okay. It would be better if we also had a z component, because it is kind of coming out of the screen, but we can't get that. You could estimate it, of course, but we'll leave it for now. The biggest thing is the fact that, remember, our camera shot is moving slightly with the train. So let's go back, and we are actually going to figure out the speed of these fence posts. So I'll go back to the beginning here. And what I'm going to do is create another data set. So I'm going to add another point series. So you can see it's come up. And if I go to make sure it's selected, now I'm going to pick, let's say, this one. So if I click on it, you can see it's moving away from us. And so on. And so now we have a new point series. So I can figure out the linear, so the x component of that second one. And it is 3.744. So we can look at relative velocities and simply figure out what the train would be from the ground frame. So we have 7.520 plus 3.744 gives us 11.264 meters per second, which is 40 kilometers per hour. Okay. And you can keep going with this, right? You can look at, say, the y component. You can use Pythagorean theorem, add them together. It's still going to be slightly off because that train is moving slightly towards your screen. So what we can do is we'll move ahead. And let's look at this car. We can figure out the car's speed. Alright, I'm going to need to set a new scale here. So let's set a new scale. Set scale for this car. Let's say it's 3 meters long. Okay, all these numbers have changed, so we can ignore them now because this is a new data set. So let's make our new point series. And we're going to start I can pick say the front tire. Now we are going to have some error because you can see the camera screen is slightly moving as well. And I've lost the tire there. But I can do a linear fit on our X. And we get about 10.5 meters per second, which is 37 kilometers per hour. These things seem to be moving pretty slowly, don't they? Well, I mean, but if you think about it, if it was actually moving at 100 kilometers per hour, just imagine if you're sitting at the side of the highway, how fast those move past you. It wouldn't really be as entertaining as a video if it lasted that long. Right? So it needs to be more dramatic, right? Which is why it's so much fun to analyze the physics of video games. Because these things are done purposely to make it more dramatic. All right. So let's say it's moving at, what do we got? Just under 40 kilometers per hour. And it gets hit. And eventually it experiences multiple forces, but eventually bring it to a stop. Now, let's say you wanted to you can't really figure out an instantaneous force. That's kind of hard in this software. But we can figure out average force over a time interval. Now, there's two ways I like to do that. Now, you could use the sum of all forces equals mass times acceleration, but acceleration is a little, it involves a lot more error, right? Because you'll have to get a velocity time graph, which you can do. You can plot graphs on this. You can also export your data there to Excel and plot graphs on that, and then find out what that would be, the slope of your VT graph would be. Another way to do it is to either use impulse, so force times time equals change in momentum, or our work energy theorem, which would be work equals change in kinetic energy. Now, whether we're looking at change in momentum or change in kinetic energy, what we need to know is the mass of that car, which we can look up it looks like a station wagon, so we can look up online an average mass for a station wagon, and its change in velocity. Whether you want to solve for kinetic energy or momentum, we know it's change in velocity. We just calculated its initial velocity, it's 40 kilometers per hour. And its final velocity is 0, comes to a stop. So we either need to know, if we're doing the work energy theorem, we need to know the distance over which that occurs. Or if we are using the impulse equals change in momentum, we need to know the time. I like using the impulse one, especially in this case, because the camera frame keeps changing, as you can see here. So it's quite difficult to figure out what that distance is. But time is quite easy. For time, I can just start a new point series, click anywhere, and then move that all the way to when it comes to a stop. Let's say about there, and click anywhere again. I click anywhere because I don't care about the position. I only care about the difference between the time of those two clicks. And you can easily look that up. All right, so right down here on our table, right, it looks like here is where the clicks occurred, and we're just going to go over and see at what time that is. So the first click was at 5.04 seconds, and the second click at 7.64 seconds. So time interval is 2.6 seconds. Okay, and you can use 2.6 seconds. Let me show you what I mean. So these were the two options I was considering. You can use sum of all forces times our time equals our change in momentum, which is the one I would like to do. Or you could use work, or total work equals change in kinetic energy, where total work is also your net force times your displacement equals change in kinetic energy. All right, well, change in kinetic energy is a half mv squared. Momentum is mv. So in this case, our average force over time is going to equal our mass times our initial velocity minus our final minus initial divided by time. Final is going to be 0 because we come to a stop. And then we look up the mass of that vehicle. We plug in that initial velocity, which was 40 kilometers per hour, but we're going to want to keep it in meters per second. And then we plug in that time interval. So let's see what we get. We'll estimate the car to be 1,500 kilograms. And the velocity in meters per second, we got to be 10.5 meters per second. And over a time interval of 2.6 seconds, I believe it was. And we get an average force of around 6,000 newtons. Okay, remember that's an average force. Obviously the force would have been a lot greater when the train hit it and when it hit the car, but that would be the average force. Okay, so that's how you would calculate these things. It's a lot of fun to think of, and if you want to see some of the other strategies that I've used to analyze video games, you can check out my playlist, which is for the analysis of video games. And hopefully, now that you know how to do this, you can go analyze those video games yourself. Have fun!